Hi, in this video I'm going to explain the fundamentals of analysis of algorithms and the motivation for it, and go through a few examples. The motivation for this, why we're doing this, really this is to look at and understand and break down the cost of an algorithm. So an algorithm is a step-by-step process to solve a problem, and really to evaluate it, we need to evaluate. Well, we could evaluate, does it actually work? Does it produce the right answer in every case all the time? That's one way to think about it, and that's an important dimension. But then the other dimension is, does it actually, what is the cost of it? How much, and that means how much time does it take and how much memory, we call it space, does it use when it's running? And this can be important so we can look at, well, typically there's a trade-off between time and space. If we use more memory, that that can mean the algorithm or an algorithm might run faster. And then also between two algorithms, if we look at, you know, method one for solving a problem versus method two, which one's better? So that means breaking down the time and space costs and comparing those. So this is important. We're going to be looking now at some important tools for breaking down these costs and analyzing them. So time is really the sort of principal cost, and so we have to think about, well, how are we understanding time with regards to algorithms. So I have these two pictures here. One on the left is a mainframe from like the 1980s or maybe earlier even, and on the right is a modern supercomputer. I have these pictures here to illustrate the point that we need a method of analyzing um, time, or how much time we're spending, that works across sort of, let's say, historical time. So if someone analyzed an algorithm and figured out its cost in 1974, we want that analysis to hold up for today. And whatever analysis we do today, we want it to hold up 50 years from now. Also, we want this analysis to excuse me, to hold up or be valid across different hardware. That's why I have another reason the picture of the old mainframe here versus supercomputer. You know, hardware will speed up how fast the algorithm runs in terms of wall clock time, but it's not going to speed it up in terms of number of steps it takes to complete the problem, or find the answer to the problem, rather. So we want the analysis to hold up when we go from computer to computer, because those are generally getting faster each year. And also, we want it to still hold up even across implementations. So if we take this algorithm and write it in C versus we write it in Python versus we write it in Rust or whatever, JavaScript, whatever, we still want the same analysis to apply. So that leads us, we're going to start talking about asymptotic analysis. And this is, in a sense, like counting steps the algorithm takes to solve the problem, not just clock time, because clock time is not going to work in any of those sort of scenarios outlined before. We can't just measure, well, how long does it take on, this algorithm take on some data set, let's say, because, next year they'll just be a faster computer, right? And I'll just cut down that time, but the algorithm didn't change. So we're going to be counting steps, sort of. It's going to be a little bit fuzzy, because again, if you really want to think about it, the amount of actual sort of clock cycles in the CPU that it takes, to add two floating point numbers together is different than, say comparing two numbers or accessing memory or something like that. And then it's also going to vary from machine to machine, different hardware, different architecture. So it's not exactly like counting clock cycles or something like that. We're going to be looking at sort of some sort of basic step, some sort of small unit of time, and then why we can be kind of fuzzy there in the sort of small step is we're going to be looking at, like I said, asymptotic analysis. So this is long run or long term performance. Really, how does the algorithm scale? That's the sort of analysis that is going to hold up kind of historically, so from decade to decade, and across implementation and across hardware. And it's an important question. So if you're, Google, Amazon, etc., and you have, millions of customers, or billions of customer interactions like every day, or something like this, you care about scale. So these kinds of questions come up all the time in job interviews and on the job, because it's a really important question. How does your code how's your code work as we just throw more and more data at it, or larger and larger problems at it? And this asymptotic analysis is going to be worst case analysis. So there's partly that will help make it simpler and more tractable for us. Also, this will just be sort of a guarantee. Along with scaling, this idea of scaling is going to help us avoid, picking algorithms that might break down in some case horribly. So we really want some guarantee when we say, this algorithm is better than the other, that there's not some sort of special case in it that sort of jumps out and really bites us. So if we kind of look at the worst case, and that's better than another algorithm in the worst case, it's a kind of stronger guarantee in some sense. Now, this is of course pessimistic. There's other ways of analyzing algorithms out there, like the Banker's method, that is more counting these sort of steps again, but it's not quite as asymptotic, and it's not necessarily in worst case. It's more going for like the sort of typical or average case. But this is the sort of most common worst case analysis. So what is this? Well, before I get to the term, just what I'm illustrating here, and what do we mean by all this is T of n here, this black line, let's say that's the actual real time. And I, omitted the y-axis here because I'm not going to worry about, exactly how many steps it took. And the x-axis is the size of the input. So, for example, if we're looking at a sorting algorithm and it's being applied to an array, the number of elements in the array, that's the size of the input. So as that increases, we're looking at the trend. What's the sort of shape of the curve? So if the black line is the real time some sorting algorithm takes, let's say, or some algorithm takes, this asymptotic analysis says we want to find really like a function that operates as a category, in this case n squared, and we want to pick this function n squared such that after some point, I'm calling called n naught, just some number. So after, let's say this is let's say a little more than 35 is the input, that blue line there, that this function n squared, it sort of dominates the true time. So well, yeah, basically after some point, this sort of category pick is always sort of worse than the true time. And again, that goes back to this worst case analysis. And also this fits into the asymptotic analysis, because we're like, after some point, we're just looking at how these things go in the long run here. And the other point here is you see there's this sort of gap between after and not, there's this gap between the two curves. And basically there's this sort of constant, let's call it fudge factor, involved. So we can say, okay, there's this maybe increasing margin between them, but that's even okay too. The point is, we're finding this category that, let's say, acts like a blanket, just sort of covering the true time. So the whole goal is to sort of find these categories, or find what category the algorithm falls into, rather. So this is going to be big O notation. And this is a definition here, and this is, a little mathematical, which scares people. But I'm using T of n as, let's say, the true time, and the sort of approximate sign there. I mean, we're going to put T of n in this big O category of f of n, so f of n might just be n squared. And we'll say, okay, there's also, we can say T of n is in this category if it meets this requirement, or we have that big O c times f of n, if there's this positive constant c and n naught such that the true time is less than f of n past that n naught. So up to a constant factor, we're good. So that sort of margin, and then n naught is that point where the sort of category function we picked, that big O function we picked, is strictly speaking greater than it. So that's again, it's the upper bound is a phrase to use for it. So if we talk about, or we think about the big O, say big O n squared, it covers after some point the whole T of n, and we can sort of use that as a substitute for the real runtime and compare algorithms based on that. So going back to that same picture, just breaking this down, that's what that n naught is. That's that vertical blue line. That's the point which sort of the category takes over and typifies the actual runtime. And again, the actual runtime's T of n, and the category we've picked for is big O n squared. And again, we're really thinking, this is just the mindset of scale. What's the long-term result as that as we move to the right on the x-axis, or that is to say, as the size of the input just keeps growing, what happens? And we're trying to find that, again, that big O that sort of typifies what happens, even if there's some sort of looseness there with that constant factor and this whole after n naught thing. So this is not a guarantee that truly in every case, big O of whatever we pick, big O of that f of n always beats T of n. It's after some point, so it's not every case. It's just really, we're just trying to take a stab at the long-term worst case for the algorithm. So what are some sort of algebraic sort of rules too that can help us in our analysis? And again, this maybe seems a little obtuse, but it's helpful. So if we have two identified time complexities here on rule 1, so we have two times are adding together, and this is the same as saying, okay, we take the big O of both sides and we just add the big O's together. So I'll go through examples on the next slide. But it's more straightforward than maybe it looks. We can do the same thing on multiplication. If you're taking the time of two different ones and multiplying them together, and then the big O of their sort of, let's say, category functions, you just multiply those together as well. Why would we do this? This will help us break down individual lines of code, as we'll see in a moment. And then finally, another important rule, rule 3, if the time category is some polynomial function, then we just take the largest degree, the term that has the largest degree. So, and sort of implied in all this too, and implied by the definition, if there's some constant term, some coefficient, we could just drop coefficients and we drop constant terms off the end. So, examples, T of n equals 10n plus 100. We're going to put this in big O n, which is linear. Um, so again, we're just dropping the 100 because that's constant. According, it's not connected to input size. That's not going to be relevant in the long run. And then based on the definition, that whole constant factor doesn't matter. So that's how we go from 10n plus 100 down to n. So that's basically using the polynomial rule, rule 3, and just the definition again to drop that coefficient of 10. Again, example 2, we have n cubed plus 100, n squared plus 38n plus 10,000. Let's use the polynomial rule just real quick, cut it down to n cubed. Pretty straightforward. And finally we have t of n equals 2 to the n, 100 times n to the 100 plus 10,000 n. Again, we're just looking for the dominant term here. Maybe this is generalization of that polynomial rule. We'll take 2 to the n here, since that dominates the whole equation. So it's exponential in time. How do we apply this to code? There's 5 rules here to sort of break it down. So the first one, basic operations, we're going to say are constant, which is big O1. So that'd be adding 2 numbers together, comparing 2 variables, accessing an element in an array, setting an element in an array, calling a function, returning a value from a function, etc., etc. So all these sort of essential steps you can think might be even implemented in the hardware, or are just a couple steps, a couple operations in the hardware. That is just a couple, CPU operations. We're going to say they're all basically the same for all the aforementioned reasons. And so let's say they're constant, big O of 1. So they're not connected to the size of the input. That's the important thing. If you're adding, let's say you're sorting, again, an array and you're comparing 2 values. Comparing 2 values is not connected to how long the array is. If it's just, you're just talking about 2 values, right? There could be 10 million items in the array. There could be 5. If you're just comparing, the first element and the second, it doesn't matter how many things are there. So that's why these basic operations are constant. They're not connected to whatever the size of the input is. The second rule, if we have consecutive statements, so you have a line of code on line 1, then a line of code on line 2, 2 different operations there. What's the big O for it? We just add those 2 together. We'll see this on the next slide too. I have an example. Anytime we have loops, we're going to simply take the complexity of the inside, all that code that's inside the loop and the body of the loop, and multiply it times how many times the loop actually runs. Often this will mean we'll just multiply the body of the code by n, right? So then we'll use the other rule to multiply those 2 time functions together, but that's not always the case. It's not always the case. It's going to be n times, because the loop might be constant, right? We could just be looping 5 times or something like this. So it's not always going to be, well, we just take the body of the code as time complexity and multiply by n, but a lot of times it will be that. So you have to be a little bit careful there. While loops in particular are tricky because it's often difficult to determine how many times we're going to iterate through there. But anyways, next rule, if we have if-else statements, we have a comparison and then maybe 1, 2, 3, etc. Blocks of code associated with the if branch. Maybe you have an else if branch and an else, etc. What we're going to do is just look at all the time functions there, all the time complexities, just take the largest. And finally, if we have a recursive function, well, this is going to be a topic for a whole nother video. We have to use something called the master theorem, because then our time function t will be recursive itself, which it will not be obvious, with the to break down, but there's a method to do this, to kind of solve it, figure out what the time complexity is. And so let's just jump into this example. Beautiful diagram here. So I have this pseudocode for finding the largest value in an array. And it's pretty straightforward, right? That we're just going to iterate through every value, compare the current value versus the max. If the current value is larger than the max, well, that's the new max, right? So we can see line 2 is constant, right? We have just an assignment, all right, that's basic operations, order 1. You could even break it down further and say accessing an elements, or the first element of array is in there. So you can say, oh, there's 2 basic operations. Again, because of constant factors just don't matter, those coefficients just get dropped. We say, okay, it's big O1. Now, because of the consecutive execution rule, we look at lines 3 through 7, and we have to break this down. So we have the for loop rule in here as well, but because of consecutive statement rule, we have order 1 plus whatever the for loop is. It's often easier to work inside out, so let's just zoom into line 5. So that's constant, because again, just an assignment. That's sort of the inner part of the. I tried to depict the sort of nesting here on the right hand side, where we have order 1 for the assignment. Now we have another order 1 for the if statement. So just the comparison of value versus max. Doing that greater than or equal to comparison. Again, it's basic operations constant. Inside the assignment is also constant, so it's a max of constant and constant. Great, it's just still constant. Then finally we get out to the for loop itself. We have a constant value from the inside times, well, how many times the for loop is going to run, which is going to be as many times as the array is long. That is order n. So if n is the size of the array, which is typically the sort of convention here, the n will be the size of the input. If we have just one input, we take basically that, since that for loop is going over every single value, it's going to take, again, n and multiply it times whatever it's doing on the inside. So then we end up with order n times O1, so we just end up with big order n for the whole for loop. Finally, we have a return statement. Again, this is constant, and the time complexity for this, we just add in another. We add it together because of the consecutive statement rule. So the consecutive statement, another way to say it is, okay, we're adding all these together, which then invokes that polynomial rule. So we just take big O of n, or we could say we're just taking the max when we do consecutive statements. Either way, you end up with the same answer. It's the same, 2 different ways, the same thing, but we get order n out of all of it. So those are the essential ideas behind the analysis of algorithms, or the fundamentals of the analysis of algorithms. Big O notation, time complexity is what we call this category, replacing each algorithm in 2. And that's it.